Recording is rolling. Welcome to Wednesday, August 23rd. So we're really going to get linear motion started in earnest here. And ways we're going to do that, I'm going to walk you guys through a lab setup. So next 2 days, Thursday and Friday, you guys are going to have this lab that involves rolling Hot Wheels cars down inclines. And I like a lot of times to introduce new topics with labs. AP encourages that also because it's almost like as if you're the scientists back in the day that have to figure out everything from scratch. Like, how does anything in the world work? Nobody knows anything, right? And then you figure out the switches. Oh, okay, this is like how it's work, right? So kind of do that, but at this same time, I don't want to leave you guys completely blank. So near to the end of class, I'm going to roll some Paul Hewitt videos. Now these videos, they're all in a zip folder. It's been on Google Classroom. Some of you guys may have, if you're really ambitious and curious, maybe already checked out some of these. I like to bring these in. I might play more of them in my other classes just because AP we got extra stuff to do. So sometimes we're a little tight on time, right? But a lot of times he might have a different way of explaining something than I would, or a lot of times he'll encapsulate an idea like in a demo in like 1 minute. Oh, that's just like so good. So I'll roll some of those today, right? And he'll take you guys through some concepts, some variables and units that you should be looking for related to linear motion. It's just going to be motion in a straight line. It could be forwards and backwards. It could be up and down. Okay? So you can have positive and negative directions going on, but I wonder what all could be involved in that. So some equation types. Okay. So next couple days lab. Thursday is going to be mostly gathering data, maybe make a couple graphs, and then Friday we're going to put the graphs together as a class. We're going to answer this question right here. So for this Hot Wheels car rolling down this incline, what equation or equations could govern the motion of this car, right, rolling down? Right, there might be a bunch of variables that maybe we want to know something about. One of the nice things about physics formulas, physics equations, is that they have predictive power, right? So once you figure this out, you can talk to the next class coming in and you say, oh yeah, we figured out, I can tell you exactly, like this car is rolled for like so many seconds or so many centimeters, like exactly how far it's rolled or what the relationship is between like after it's rolled so much time, how far it's going to roll, right? You can know that, right? Maybe it has something to do with this angle of incline. Maybe it has something to do with the gravity field. Right? Maybe those could be like more general equations to use that too, right? Right. Also remind you guys, last couple of days, you guys been working with trigonometry and vector components, and you guys have had this page. So this page is going to be due on Friday. One side is like the science empiricism side, where you get to break out the ruler and the protractor, make some measurements, and also some calculations. And hopefully your calculations are lining pretty close with your measurements. Right? I said pick any 3 of the 5 triangles. Right? Just ignore the other 2. Right? So any 3. Okay? And on the back side of this page are 10 trigonometry puzzles. They're all related to right triangles. And every one of these is a unique situation. I really want you guys to be able to navigate your way around a triangle. That's trigonometry, yeah, all over the place in physics. That'll definitely help you guys out. All right, so you guys okay with what we're doing, where we're going? You guys good? All right. So let's take a look at this. All right, I've got this Hot Wheels car. I'm gonna roll it down this incline. Tell you what, if you're in class, do you guys see back in the lab area? You guys see that metal incline that's already at some angle? You guys see that? That metal one, right? Right. So okay, so you guys are gonna get some set up like that tomorrow, right? And we want to figure out, like this car rolling down, right? See, like if we were out in deep space, we're just like floating around. If I put this car here, it's just gonna like float around. So that's no fun. Right? But down here, where we've got some kind of gravity field, this car is gonna move. How does it move exactly? Actually, this is very similar to a set of experiments that Galileo did back in the day. You guys remember Galileo actually precedes Isaac Newton by a few decades. So not only was he dropping stuff off Leaning Tower of Pisa, not only was he looking through a telescope, seeing, oh yeah, moon, there are moons that are orbiting Jupiter. Whoa. He was also taking, actually, his version was he took balls and he let balls roll down inclines. Right? It's kind of like a slowed down version of free fall. So maybe like the, right. So what variables could we be possibly juggling with this scenario? What's one variable? Do you guys think? One variable. Yeah. What do you think, sir? Good. All right. Yeah, the angle of incline. Actually, I'm glad you're starting with that one right there, because this one right here, the angle of incline, we're going to leave this lock in place. Let's say we're going to leave it controlled, right? Like control, right? That's going to be true for everybody. Now, a few weeks from now, maybe we'll change the angle of incline, or say like, if you change this angle, how would that like change the motion of the car? Because it would have an effect, right? Right. Yeah. Here. So if you guys are looking at that that incline back there, if you guys just had to eyeball it and make an estimate just by eyeballing it, how many degrees from the horizontal do you think it is? About? Had to guess. I'm hearing a 5. I'm hearing a 15. It's probably somewhere between there. Somewhere between 5 and 15. You guys think? maybe 10, maybe. Right? Now tomorrow, right, you guys take your protractor. You've been using a protractor the last few days. Right? You can measure it and get it for sure. Right? Now that'll be just control for slab. Once you have it, it's supposed to get like 7 degrees. Just go ahead and leave it locked in place, 7 degrees control for you and your teammates. Yeah, Steve, what are you gonna say?
I was gonna say the length of the incline.
Oh yeah. How about this distance x, right? And to measure that, so you could use a roller for distances or displacement. You could use a meter stick. Now that incline vector, I tell you what, it does have like a meter stick function built into it, right? Actually, it's like 2.2 meters long. I think is how long it is, right? So you guys get like over 2 meters. You can allow this car to roll, right? Now that's probably related to some of these other variables. What's another variable that you could be working with? Yeah, gravity field, right? Now, since we're all stuck at the surface of Earth, that we can't really change. So that would be a control. But that is a good idea to keep in mind. Now, if we come up with some master equation that could answer this, yeah, if you really want a general equation, the gravity field would be part of that. So you could take this to the moon and see like, ooh, how does that go on the moon? Yeah,
the mass of the car.
Mass of the car. Yeah, I have that labeled M, mass of the car. Okay? Let's do some hypothesizing. Right? Come back to this idea later. Right? So I got like, maybe a small mass car here and a large mass car here. Right? Their mass is like how much inertia. So like if I push these back and forth, this guy really easy to change its state of motion. This guy, really hard to change its state of motion. So much mass. Notice I'm not picking up the weight. Weight's like a downward force, right? Look at like the mass, right? Oh, actually, but before we get to hypothesis, measuring tools. I got to do measuring tools with you guys. AP cares a lot about measuring tools. I'll talk about that later. Okay. So 2 ways you can measure the mass of this. One is with this digital scale right here. Now this is not plugged in yet, but if it is, you might put this car on here and it might say, just make something up, like 33.51 grams, which would be a lot of precision, wouldn't it? 33.51 grams. Woo! That's like getting really precise. Okay. Now, if you take this digital scale to the moon and plug it in on the moon, then will it still give an accurate reading for the mass? Will it still say 33.51 grams?
Yes.
You're correct to say no. If you said no, you are correct, right? Because the way the scale is actually working is what it's directly reading is actually the weight, like a downward force, because there's downward force on this car, it's weight, right? And then it's saying, well, must be used at the surface of Earth. So given that we are at the surface of Earth, what mass would have caused that? So it's dividing by Earth's gravity field, and it's telling you what the mass is, right? So really it's reading weight and telling you what mass would have produced that particular weight, right? You guys get that? Right. Yeah, so on the moon it would read something that's too light, but the other tool you could use to measure mass is this guy right here, a triple beam balance. Guys, this triple beam balance. Show hands. How many guys have ever used one of these triple beam balance? Ooh, most of the class. Nice. Okay. I'll give you guys a refresher or maybe an intro. You've never seen one before. Okay. Trying to get a video shot of this. Right. Got a confined space here. Right. But if I turn sideways, sort of. Right. So this is kind of like a seesaw, like a teeter-totter, a seesaw, like on a playground. Right. Works on the same principle. Works on a principle called torque. We'll talk about like in December-ish. Right. But I can put some object on this plate over here, and it's gonna like unbalance the seesaw. And before I put on anything at all, this should be kind of like balanced, like right. See, this could like here, but it should be kind of hovering around here, like it's all zeroed out. Right? If it's not quite zeroed out, you might be able to recalibrate it by twisting this knob back here. But right now I got it pretty well calibrated, so I'm gonna go with this. Let's check this out. Let's say I pick the heavy guy. No, let's do the master car. How about that? Let's do the master car and how much this guy is. Okay. So put this guy on here. Oh, and it disrupts the balance. So this is no longer balanced. It's out of whack. Okay. I have 3 sliders. I got a 100-gram slider, a 10-gram slider, and a 1-gram slider. Okay. So maybe I'll choose a 100-gram slider and see what happens. Oh, that was too much. This car is definitely less than 100 grams. So slide this guy back. Slide this guy. Let's go 10. 20, 30, it's more than 30. Let's see, how about 40? Oh, 40 was too much, it tipped the scale. So let me slide this back to 30. Now take the 1-gram slider and just do 1 gram at a time. Until, ooh, right now everything's just balanced out. That right there is reading about like 33.7, I think, 33.7 grams. So a blank car, probably about that, right? Maybe every car's a little bit different, but probably about 30 something grams. Okay, let's try the big guy, just for fun here real fast. Okay. Zero this all out. Okay. The 300 is too much. 200 is not enough. Let's try 250. Too much. 240, too much. 230, ooh, not enough. It's about 234 grams. You guys see that? Right, like bounces out. Right. Now, if you took this to the moon and you use that on the moon, would this still say 234 grams? How many guys say it would? It would. Ah, yeah, there's my winners right there. Yeah, yeah. Because you say, wait, on the moon, this has less weight, and some do with weight. But remember, these sliders also have less weight. Ah, so it balances out. So as long as you have a gravity field, it doesn't matter the strength of gravity field, this will still give you an accurate mass reading. Ah, pretty good, right? Nice classic analog triple beam balance. All right, so we got that. Check. What have we not mentioned yet? I'm thinking at least two things. What and what? What's one of them? One variable. Yeah. What do you see? Time. Tick tock. Oh yeah. So how much time has this thing been rolling for? I got you guys a brand new set of stopwatches, so that you guys don't really have to worry so much about pulling out your phone. So we got stopwatches now. Now time. This one's the trickiest one. Like especially if like so some of these time intervals might be like less than a second possibly, or maybe a little bit more than a second, right? So getting the time like exactly, like start stop like exactly, it's probably hard to get it exactly accurate. What's a good way? Sometimes you're a little slow on the stopwatch, and sometimes you're a little fast. What's a good procedure you can do? I think so. Ooh, bam! Exactly. Right. Take like multiple trials, right? Multiple runs and take an average, right? That will help reduce random error. If sometimes you're a little fast, sometimes you're a little slow, it'll kind of even out, right? Now, it's not so good at addressing systematic error if you're like always getting long time intervals, like, well, okay, not so, but random error, yeah, definitely. Right? A little bit above, a little bit below, right? And tell you what, that right there, that is worth one, it's always 1 point on the AP exam. AP exam in May, one of your FRQs is going to be experimental design. They want you to do a lab write-up. And one of the points is always do multiple takes and take an average, right? So got here, start, stop, reset. And it says that exactly on the page, how to do that. All right, so we got time. Okay. And there's one last variable I have listed on this page, which is velocity, like speed. You can say speed or velocity. Speed is like the magnitude of velocity. Okay? I'll talk about that a little bit more later. Actually, I got a couple of those. I got V naught, which is like initial velocity, which is just going to be 0 meters per second because you start this from rest. Right? Anything you start from rest, car there, let it go. It starts from rest to 0 meters per second. It's going to be going. Okay? Remind you guys, the very first day you guys walked in class, one of the pages that I gave you guys have this. It's a page full of variables and associated units. Right? Different types of velocity. V is velocity or speed, you could say. Okay? If you see V sub naught, or sometimes some textbooks use V sub I, right? It's like an initial velocity, right? That's like the velocity at the beginning of the interval. If you see V sub F, that's like the final velocity. That's like the velocity at the end of the interval. Hey, I wonder if this car has all different speeds as it's going down the track. Possibly. Maybe that makes sense, maybe, right? But in this class, all you care about are two instantaneous values: the speed at the very beginning, which is going to be 0 in this case, 0 meters per second, and the speed at the end, which will be final velocity. Right? All the ones in the middle, don't worry about so much. Right? The only ones in the equation are those in the equations are those instantaneous velocities. Now, how are you going to measure those instantaneous speeds? I'll give you guys a couple of options. One is this right here. I'll call this a speed gate. Okay? So the way this is working is, ooh, look at that. Looks like a gate type shape. In fact, it'll just fit a Hot Wheels car. You can just go through it. I think that's what it was designed for because you can pop this straight onto a Hot Wheels track like this. Okay? So it's got a couple of sensors in it. And as this car kind of drives through, then say, okay, the car was here at this time and here at this time. So if it knows the change in location divided by change in time, it can calculate how fast it's going. Right? Technically, it's an average speed over a very tiny time interval, but that's getting pretty dang close to approximating an instantaneous speed, isn't it? Let me show you guys an example. Turn this on. So that, okay. Right now it's flashing the unit, so, whoops. Second. Centimeters per second. Centimeters per second it's saying. Second. Right. So let's have the car go through. Let's try again. Hey, come on, doing sound effect. Now you gotta work. There we go. 136, it's saying centimeters per second. If you want to change the unit, you can, I think, like mash this button. You can do meters per second or kilometers per hour. Centimeters and centimeters per second is fine tomorrow. Okay. 136 centimeters per second. You see it? Okay. So this car goes through. Right. So maybe you can like put this on the finish line now. Goes through. Right. You guys good there? There's another way you can measure speed too. Right. That's this guy. Now, last year, the school got a brand new set of these. Now, this is a motion detector. I have to turn it on like that. If you guys want to use this tool, I'll let you guys figure this out. We were trying to use these last year. I was trying to get them like connected to the laptops and stuff. It was the whole thing. It wasn't really working. But I figured out over the summer, went to a conference. They showed that if you download this app onto your phone called Graphical Analysis, here's the company that made this thing, Verdier, I think. I think that's pronounced it. Right. Graphical Analysis. It's an app on your phone. Then this can tell you the displacement of the car as a function of time, the velocity of the car as a function of time, so get speed if you want to, and also the acceleration of the car as a function of time. We'll talk about that later today. So a lot of information you can get. And when you turn it on too, it sounds like echolocation, like bats. It sounds like, right? You can hear it. Right? It's like gathering data, sorry. Right? So this one would require your phone. If you have your phone out tomorrow, it's because you're using this equipment, right? But everything else, you don't need your phone. All right, you guys got that? Okay. Now, why am I making a big deal about all these measuring tools and whatnot? Okay. Again, I told you guys AP will expect you to do a lab write-up as one of your free response questions in May. It's part of the exam. Right? They're going to throw this only problem at you. It might be this lab, right? Oh yeah, that's like one of the first labs we did. Right? Just right. Right? And there's always like this 5-part procedure they have you do. Let me find the page for that. There's always a 5-part procedure. Okay, it goes like this. What question are you addressing? List the measuring tools that you need to address blah, blah, blah. Right? Some procedure, like briefly describe the lab setup, and then what are you using each measuring tool for? And then, hey, like maybe take multiple takes in an average, right? Analysis involves graphs, what we'll get to this lab, and then some kind of conclusion, which usually involves some kind of equation going on, right? So maybe it's a good idea to know like what measuring tools are you can even draw from. Right? In this class, here's like some common like high school measuring tools. There might be a couple other ones, but just the ones that all the ones I could think of the other day when we put this together. Okay? So meter stick or ruler can measure displacement. Right, here's some possible units for those. Protractor can measure angles in degrees. Stopwatch can measure time in like seconds or milliseconds. Or motion detector. This is one that AP likes to use a lot in its rubrics for these type write-ups. Right? So this could be displacement, velocity, or acceleration. That's this guy right here, right? I do need to fix this. This is just for velocity. Meters per second is velocity, right? I need to amend this a little bit. Triple V balance I showed you guys. Digital scale I showed you guys. Some way of measuring mass. Spring scale. I have a couple of spring scales around here. You could measure force. So if you like hang something from these spring scales, right? The heavier it is, the more it stretches the spring. In fact, that's a direct relationship. If it's like twice as heavy, it'll stretch it twice as much. That's called Hooke's law. Okay, so it can tell you in newtons what's that force. Voltmeter and ammeter are to measure voltage and current for electricity. I might pull those out like 1 or 2 days next semester, but those are not going to be on the AP exam for you guys. Okay, right. So I have this poster hanging over there on that wall, so you guys can reference that, but probably a good idea to have those tools in the back of your mind. So when you get that FRQ, like, oh yeah, got these tools, can measure these things, do this stuff. Right. All right. So lots of variables juggling around there. Now, a few days ago, you guys told me if you have a really well-designed experiment, ideally you want how many independent variables at a time? Just one, right? One. All right, that's my winners. Well, we got so many variables going around and somehow need to feed some kind of master equation. Ooh, how are we gonna do that? Well, we probably need to split you guys up into like do separate experiments, right? Like some of you guys are controlling this and changing this. Some of you guys are controlling this and changing that, right? So the way I'm gonna do this is when you guys walk in tomorrow, I'll have you guys back in teams, okay? And I'll throw a playing card on your desk that's gonna have one of these suits. And whichever suit you have tells you which experiment you're gonna do. Let's do 4 different experiments, okay? And then we'll bring it all together as a class and make some giant master equation. Okay? So if you have the clubs tomorrow, I'm gonna have you test for mass, like mass as a function of time, right? So if you change the mass of the car, how does that affect how much time it takes to go down the incline? Now, if you have this one, you want to control everything that's not one of those variables, right? So for example, the angle of incline, but that's true for everybody anyway, right? We're not going to worry about the angle tomorrow. Right? Everybody's going to lock in their angle. If you have 7 degrees, just leave it 7 degrees the way through. But the distance, the rolling distance, Right? So if you have the clubs and you roll your car 200 centimeters, then every time you roll the car, it's going to be 200 centimeters. You guys got that? You're going to control that. You're going to control it. Okay. You can swap out the mass of the car by taping these lab weights. Got whole boxes of lab weights you guys going to have. You just tape them to the car just like this. You guys get that? Right? Right. And say, how is that going to affect how much time it takes to go down? Right. Let's do some hypothesizing. You guys ready to hypothesize? Right. I'm going to see show of hands. Let me give you guys the example of the options first. Right. So as you go from a small mass to a large mass, from this guy to this guy, small mass to large mass, you're increasing the mass. Right? Suppose we have this distance at like 200 centimeters. Right? This car goes around and down in like some amount of time. Right? This car right here with more mass is going to take more time to reach the bottom of the incline. Say it slows down. Less time to reach the bottom of the incline. It's a little quick eye. Or if you put these two guys side by side, would they pretty well tie? Right? Show of hands. How many guys think increasing the mass takes more time to reach the bottom? Who says that? More time. Who thinks increasing the mass takes less time to reach the bottom? And who thinks that these two side by side would pretty well tie? Who thinks that? All right. So you see different votes or different hypotheses floating around. You guys are going to find out tomorrow with the votes. Right? If you have the spades, you're going to look at distance versus time, in which case you would be controlling the mass. So you might just like run a bunch of blank cars, right? Just whatever it is, control for that. Right? Right. All right. So try different distances. So you guys say, hey, let's do 100 centimeters, 120, 140, 160, 180, 200 centimeters, right? So, and then how much time does it take for each one of those? Maybe do 3 trials of each one, take an average kind of deal. You guys do that? Okay. All right. Now, obviously, the further it has to go, it's going to take more time to do that. Right? But I want you guys to figure out exactly what is that relationship. Let me give you guys 3 options, and let's do another hypothesis. Right? First option is maybe there's a direct relationship. And what that means is like if you double the distance, it would also be double the time. So if you go from 100, let's say 100 centimeters took 1 second to roll down. Oh, so at 200 centimeters, given the mass and the angle, it should be like 2 seconds because that would be double. So double, right? Second option, maybe if you double the distance, it takes more than double the time. Third option, maybe if you double the distance, yeah, the time will increase, but it'll be less than double, right? All right. So show of hands. How many guys think direct relationship? If you double the distance, it'll be double the time. How many guys think that? Anybody think that? How many guys think if you double the distance, it'll be more than double the time? How many guys think if you double the distance, time will increase, but less than double? How many guys think that? All right. So good hypothesizing on the board. All right, if you have one of the red suits, the diamonds or the hearts, at a glance, these are going to look pretty similar setup, but I want you guys to measure slightly different things. Let's start with the hearts here. Start with hearts. Right? So speed versus distance. Now this is, of course, controlling for the mass and the angle. Right? So you'll let the car roll different distances, and then you're going to gather the speed. Suppose you want to use the speed gate right here. Right? And you see what are the speeds after it's rolled. Say 100 centimeters, it's rolling in. Say 150 centimeters, and then 200 centimeters. It's rolling all these different distances. What are the different speeds? Right? I bet if it's rolling further, it's rolling faster. But again, kind of like with distance versus time, is that a direct relationship or is it something else? Right? And then diamonds, speed versus time. Okay. Now, at a glance, again, these will be very similar setups because for rolling different times, it will also roll at different distances too. Right? So that's kind of how these are in common. Right? But you're not really keeping track of the distance. What you are doing, if you have the diamonds tomorrow, is you're with the stopwatch. So you're letting it roll and like start, stop, and then it's stopping. You're stopping the stopwatch right as it's rolling through the speed gate, for example. Right? And then go back and let it roll. Yes, a different distance, but you're really like timing with the stopwatch and recording that. Okay. And then, oh, hey, I wonder if these two guys have a direct relationship or something different. Right? You guys gonna get that? Right? Any questions so far? That's all right. All right. So that's gonna bring us to this here table, this table. As you guys were walking in and I was taking attendance, you guys were copying that table down. Thanks for that. Give us a head start here. So you guys wrote your name on your paper, right? Also, if you want to keep all your labs in a notebook, some of you guys brought composition notebooks. This is a good one for that, right? Don't have to. If you want to compile your own book after the fact, then that's good too. So either way, you guys have a title, car and incline lab. Incline angle is blank degrees to the horizontal. Ooh, notice I specified to the horizontal, right? You don't just say blank degrees because someone else could pick up your lab paper and say, is it to the horizontal or is it to the vertical? Sometimes in this class, you're measuring with respect to the vertical, sometimes with respect to the horizontal. this case, the lab table is horizontal, probably makes intuitive sense, like 7 degrees, for example, if that's what you measure, 7 degrees from the lab table, from the horizontal. Right? Okay. This table, ooh, lots of columns, lots of rows. What goes in these columns? Well, it depends maybe exactly what experiment you're doing tomorrow, what version, what variables you keep track of, right? You want to measure some things, even if they're controlled variables, and they'll just be like the same thing all the way down. Okay, let me show you guys the prefabricated version of this lab table. Okay, now one reason I did not go ahead and copy and print these out for you guys is because ideally AP wants you guys to just start with blank paper, like just like I can pose a question, I can throw some blank paper at you and say go figure everything out. Okay? So they want you to figure out, like actually like, use your mind to figure out what variables and units are you going to have to keep track of the whole deal. Okay? Also, when you guys do an AP write-up, I'm going to have you guys do an AP write-up, and then we'll look at those on Friday too. Okay? Just one thing I've seen over the years, just having taught so many years, is sometimes students will write the step like, step number 3, record the data and the table. Well, right, in AP world, there is no like the table, right? There's like, you have to kind of figure out everything from scratch, right? So there's no like the convenient table that was printed out. Okay? So this is how like I might put together a table though. And actually, I would probably even extend this because over the years I've extended it to like those 4 experiments. Okay? This is a little bit limited. Okay? So I got different trials going on. Oh, hey, look at this, like 3 trials and an average, 3 trials and an average. You guys see that? Like, especially if you're using that stopwatch, like especially stopwatch, right? Right. Maybe like what distance in centimeters. Oh, no, there's a variable and a unit, right? Like if you just see the number 3 on a paper, we're talking about 3 kilograms, 3 pollutions. What are we talking about? Oh, 3 centimeters, right? Right. So variable unit, right? Mass measured in grams. I know in this class we usually use kilograms. That's your go-to mass, right? But grams is okay tomorrow because little tiny toy cars. Okay. Oh, measuring time. Again, with the stopwatch, especially, like, do 3 and take an average. These will be in seconds, right? So measure time and then average time for those 3. Okay. And then, ooh, what's this last column? Average time squared in square seconds. Okay. Now, this is like a manipulated variable. This will make sense before the weekend. Like right now, it's like, why would you square the time? Right? But you guys will see, it'll help make some really nice looking graphs where you can very quickly whip off an equation and tell something about what's going on. There's a process that AP loves called linearization. You're going to do it lots of times. This class is one of the first times you get to do it. Actually, I wanted to do it with that circle activity. We never quite got around to, but maybe on some rainy day I'll get to slip that in. But hey, look what we got. We got distances in centimeters, masses in grams, times in seconds. That's too many variables. You have to control something. And this particular version of the table, notice I put some tiny hash marks all the way down underneath the mass column. Okay, that's like, the intention there is like you be controlling for the mass. Like whatever mass car you're using, you just use the same mass all the way down. I guess that, right? Oh, so that could be the control here. And then I'm looking for what's the relationship between like distance and time. Right? Hey, maybe that time squared could help make a graph that gives some kind of insight. Okay? Which you guys will see by the weekend. Okay, right. You guys good? All right. Back to this blank table though. Right? Because you guys have a blank table in front of you, because you don't know at this moment exactly which of these 4 experiments you're going to be doing tomorrow, but you'll be able to, you'll be ready to field any of those. Okay? So some variable and some unit in each column. You might have a spare column or 2 at the end, which could be helpful. Let me pause this. All right, recording is resumed. There we go. All right, so sometimes it's nice to have a couple of spare columns. Sometimes there's a variable that you didn't think to record before. Hey, I wonder what that variable is doing. Hey, let's keep track of it. Oh, I have a spare column. Or sometimes you might want to manipulate one of your axes in the eventual graph. So you have times recorded, you want time squared, so you can do fun stuff with that. Okay, you guys kind of get that? All right. All right. We got next here. I'm eventually gonna have you guys make these 6 graphs. So just flashing this in front of you now, just so you can start taking up these. Right. Now you and your teammates won't be able to do all 6 with your own data. You might be able to do like 1 or 2 of these. Right? But as a class, we'll put all 6 together, and then we'll figure out like some mass equation that's governing the motion of the car. Right? So got mass in grams versus time in seconds. Oh, look at that, variable unit, variable unit. Ah, you guys see that? As all your graphs are going to have some variable and unit. We got to know what we're measuring and how we're measuring it, right? What's rules for what variable goes on which axis? Like in general, what variable goes on your horizontal axis? Independent or dependent? Independent, right? That's a rule for graphs, right? Independent goes on the horizontal axis. But hang on a minute, this looks backwards, right? If you're looking at mass as a function of time, wouldn't you be switching out the mass of the car? That's kind of like independent. And the resulting time is kind of like dependent because there's another rule that says if time is ever involved, then as a rule, you put time on the horizontal axis, and that rule overrides the other rule. Okay, I guess that. Okay. Similar thing with displacement versus time. Oh, look, displacement in centimeters versus time in seconds. Right, so you might be changing different distances and getting different time. Okay, right, guess that. Okay. Right. I asked you guys to hypothesize before what these graphs would kind of look like, right? Like, is this graph slope up, slope down, or like would be constant, or like no relationship? This one, does it go up like linear, like direct relationship, or does it kind of curve down like this, or kind of curve up like this, right? Distance versus time squared. Okay, so distance in centimeters versus time squared, which would be in square seconds. It's kind of an abstract idea, but there's going to be an interesting type graph that comes out of this. So it's going to be it's really fundamental to what AP wants you to do down the line for a bunch of different type graphs. You guys are going to see what this graph looks like. That's quite interesting. But I'll leave it at that. Okay. Final velocity, like as it's crossing the finish line in meters per second or centimeters per second, right, as a function of time in seconds. Final velocity in centimeters per second is a function of how far it's rolled in centimeters, x in centimeters, right? That one of those was diamonds, one of those was hearts, right? And this last one is also a manipulated axis graph. The velocity squared as a function of distance in centimeters. Right. Again, that's I know what the result's going to be, so I know it's going to be a useful graph. Okay. Right. You guys okay with that? Okay. So we're eventually going to make those graphs. Just wanted to introduce the idea to you. You guys know where this is going. Okay. All right. So we're back to this. I flashed this up here before. AP style write-up. Now I did this 5-part write-up. I did post a file to Google Classroom. I think it's in the first week materials that says pretty much exactly this. Right. So reminder of why we're doing this. In May, when you guys get the AP exam is in 2 halves. There's a multiple choice half and there's a free response questions half. The free response questions, one of the free response questions is always a lab write-up. They throw you some scenario. It might be this lab we're about to do tomorrow. Okay? They say, how would you design a lab and go about and figure out blah, 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 right? Motion of a car down the incline, right? Right. So like, what is the relationship between blah variable and blah variable for a car rolling down an incline? There's 4 different experiments going on tomorrow. Right? They always ask, what measuring tools are you going to use? You say, oh, well, I'm going to use meter stick to measure distances, the stopwatch to measure time, and maybe the triple beam balance to measure mass of the car. Right? Okay. They ask for a procedure, and you want to briefly describe the lab setup, maybe just in a couple of sentences. Oh, well, I'm going to set up an incline and set the car at the top and let it roll down. Right. Maybe use the protractor to measure blah, blah, blah. And they're always looking for this. What tool do you use to measure each variable? Right? Each variable, what tool did you use? Okay. Think from an AP grader's point of view. They have a grading rubric in front of them. They're saying, oh, you've got that tool, check, you get a point. That tool, check, you get a point. Oh, you use that tool to measure this, check, you get a point. Right? Oh, you took 3 trials and you took an average. Oh, you just reduced random error, check, you get a point. Okay, great. Picking up some points. Okay? Analysis is usually some form of graphs. Like, what graphs did you make? What variable and unit did you put on each axis? Right? And sometimes they're looking for a manipulated axis. Right? By the time you guys take the AP exam, you're going to be really familiar with what are the equations, right? What should these graphs look like? Like, you're going to know going into the exam. And so you're going to tell them, oh, I would definitely make this variable on this axis, this on this axis. And I know what that graph is going to look like because we did it in class. In fact, I did that lab myself. Okay. Right. Conclusion. Again, it's usually some kind of equation. What equation could we have that's going to tell you how far the car rolls as a function of like time and maybe how massive it is, and later on in the year, maybe what angle it's at, okay? And what gravity field we're in. Okay, right, you guys got that? All right. Questions so far? You guys doing good? All right. So let's flip over to Paul Hewitt, and Paul Hewitt's going to tell you guys some things to think about with linear motion.